Okay, let's begin. This is going to be empirical and molecular formulas. Now, for an empirical formula, the difference between the two. Is a chemical formula with the lowest whole number ratio. The molecular formula is the actual whole number ratio, not reduced. So let's say, just for example, I had a molecule that was C4H10. Jade, can that be reduced to what? So now you say it can't be reduced. Look at numbers 4 and 10. She says C2H5. So it can be reduced to C2H5. That is correct. Can it go any lower than that? Not really. So based on the definitions here, Jade, which one is the empirical formula? C4H10 or C2H5? That's right. The C2H5 is the empirical formula. And the C4H10 is the actual formula that's not reduced. This is known as the molecular formula. I'll give you one more. How many of you remember what the formula for glucose is? What is glucose? Do you recall? Nicole? C6H12O6. That's glucose. Can that be reduced? To what? Now, do we say C1? It can be reduced to CH2O. That is correct. So, Scout, which one is the molecular formula? C6H12O6 or CH2O? That's right. The one that is unchanged. That is your molecular formula. And CH2O is your empirical formula. All right, so that's what we're going to get to, and what you guys are going to learn how to do today is how to actually get the empirical formula from just raw data with moles and grams and all that stuff. So in order to do that, we got to work our way there, and the first thing we're going to do to work our way there is going to be called percent composition. Percent composition is basically determining the part, how much a part makes up of the whole. You then multiply that by 100 to get the percent composition. So I have an easy way to think of this. Let's look at, let's see, four guys here. Colby, how much do you weigh in pounds? 150, okay? Colby is 150 pounds. Plus, Adam, how much do you weigh? 158 pounds. Okay, let's keep it going. Max, how much do you weigh?
125.
And lastly, let's do David, how much do you weigh?
130.
Okay, so let's figure this out. Hey Siri, what is 150 plus 158 plus 125 plus 130?
150 plus 158 plus 125 plus 130 is 563.
So 563 is the whole, okay? This is a part, we can call that part A, part B, part C, and part D. You add up those 4 parts, you get the whole. I want to know what percent max makes up of 563. How do I do that? Arshan? You do max's weight divided by the total. That's all. So we do 125 pounds. Remember, no naked numbers. Divided by 563 pounds. The 125 is max's weight. The 563 pounds is the total weight. And we are going to multiply that answer by 100 so that we will actually get it as a percentage. Siri. Hey Siri. What is 125 divided by 563?
125 divided by 563 is about 0.222.
So 0.222 times 100 is 22.2%. Max's weight makes up 22.2% of the 4 boys together. Just shy of a quarter. That is known as percent composition. Now, let's put it in terms of actual chemistry, okay? You have a 100-gram sample that contains 55 grams of element X and 45 grams of element Y. What is the percent composition of each? Nick, what is 45 plus 55?
100.
100 even. It says you have a 100-gram sample. So Nick, I want to know what percent element X is of the total 100 grams. So X plus Y equals 100 grams. I want to know what percent is element X, what is its percent composition? So how do we figure that out?
Oh, since it's 100, it's going to be 55.
Yeah, there's a reason I chose 100. It's going to be simple. So for element X, you're going to do 55 grams divided by 100 grams. And as Nick said, oh, it's because it's 100. This is easy. Nick, what is 55 divided by 100?
It's 0.55.
It's going to be 0.55. You multiply that by 100, and that will get you 55%. And for element Y, Jade, it is 45 grams. How do I find out its percent composition? 45 divided by 100 grams equals 0.45 times 100 equals 45%. That's how we find percent compositions. Now, let's figure out calculating percent by mass and learning the percent compositions there. Are there any questions so far with what I've done? Does anybody here play baseball or a fan of baseball or watch baseball? So what's your favorite team? Perfect. I like you already. Let's say that you're watching a Rays game, and one of the Rays' more famous players is Kevin Kiermaier. He's actually kind of my neighbor. Let's say that he's not a great batter. Let's say that his batting average is about 233. You hear this number a lot in baseball. You know, batting average is 300. Batting average is 233. Well, what that means is if you multiply it by 100, he's hitting the ball 23.3% of the time he's at the plate. That's what that number means. And in baseball, if you want to know, 300, when you're batting 300, that's 0.300, which is actually 30%. You're hitting it a little less than 1/3 of the time. That's actually considered good. Baseball is the only profession where you can be good 1/3 of the time. and still be considered successful. You know, if that was a school test, that'd be a really horrible F, 30%. But in baseball, that's considered good. So that's how we use percentages. If you ever heard the term in sports, oh, their record is at 500. That's their winning record. You multiply that by 100, that's going to be 50%. They've won 50% of their games. That's what they mean by, oh, their record is 500. All right, moving on. Let's do calculating by percent mass. Or calculating percent by mass. I think you guys are going to do, I think you're going to be able to handle this one pretty, I have good feelings about this. I want to know what is the percent composition of sodium hydrogen carbonate. Calculate the percent composition of NaHCO3. Okay. So the heck do you do with this? I'm going to give you the tutorial here, and then we will do another practice problem with calculating percent by mass. So step one, I want you to find out the percent composition, or the percent by mass, of everything in this compound. You have sodium, you have hydrogen, you have carbon, you have oxygen. The first thing you need to do is you need to determine the molar mass. Determine the molar mass of A, each element, and B, the entire compound. So let's do that. Let's kill two birds with one stone, okay? Kevin, what is the first element you see in this compound?
Sodium.
Perfect. Can you tell me what is the molar mass of sodium?
23.0 grams.
Very good with your unit of measurement. Nice start. I don't like saying, of what, Kevin? I didn't have to say that. Good job. He said 23.0 grams per mole. Kevin, how many moles of sodium are in NaHCO3? That's right. So we need to multiply by 1, which is pretty redundant. There we go. Perfect. Thank you. Jade, what is the next element that you see in NaHCO3? Hydrogen. What is the molar mass of hydrogen? 1.0 grams per mole. How many hydrogens are there? How many moles of it? Very good. So we'll just make that 1.0 grams per mole. Juliana, what is the next element that we see in this compound? Carbon. What is its molar mass? 12.0. You need to go to the tens place. 12.0 grams per mole. How many carbon moles are there? 1. So we'll keep that at 12. And lastly, let's see, Kendall, what is the last element that you see in the compound? How many oxygens are there? All right, we'll get to that in a second. What is the molar mass of oxygen? I really want you guys just to memorize this number. Have you memorized it yet? 16. Good. 16.0 grams per mole times what? How many oxygen moles are there? Times 3. What is 16 times 3? 48.0 grams per mole. Nice. Okay, now, you guys now have all their individual molar masses. Let's add that up. Let's see, let's just see if we can do mental math here. We got 23 plus 12 is 35, plus 1 is 36. What's 36 plus 48? Yep. Okay. That's the total molar mass. Terrific. So you now have the molar mass. I want you to determine what percent each element is of the total. So for sodium, or this is step 2, calculate the percent of each element in the compound. Okay, so for sodium, sodium is 23.0 grams per mole divided by 84 grams per mole. Carson Cheeseman, I need you to help us with this one. What is 23 divided by 84? Times 100. Don't forget that.
Okay. I got 27.4.
27.4%. Okay? Carson Dye, you're going to do hydrogen. What was the molar mass of all the hydrogens in that compound? 1.0 grams per mole divided by 84. Okay, don't forget to do times 100. What is 1 divided by 84 times 100?
1.2%.
1.2%. All right. Yes.
Is there any units?
No, just percent.
Can you just grab the
Yep. Derek, I'd like you to hit the next one here. What was the molar mass of carbon? 12 what, Derek? 12 grams per mole divided by the whole 84. What is 12 divided by 84 times 100? 14.3%. And the last one, Emma, what was the molar mass of the 3 oxygens?
48.0.
Good. Divided by 84 times 100. Tell us what it is.
Um, 57.1.
Oops, 57.1 you say?
Yeah.
Okay. I'll take y'all's word for it. Now, who have I not spoken with? Tim, I need you to double check our work. How can we prove that these are right? What should all these add up to? Okay, can you do that for us? 27.4 plus 1.2 plus 14.3 plus 57.1. It should equal 100. I hope so. It does? Right on. It's perfect. All right. So, clearly oxygen is the bulk of that compound. That is how you calculate percent by mass. And now, for an actual problem for you guys to do on your own, I'm going to kick the birds out of the nest. You're going to fly or fall. Determine the percent by mass of, let's do phosphoric acid, H3PO4. I'll give you 4 minutes. That should be enough time. You have your script, use it. If you're watching the video, do your work now. You can take, or you can fast forward to when I go over. Francis, what is phosphorus? 31.0. All right. Yeah. Oops. Thanks for catching that. Grr. Okay. 3.1 plus 31.6 plus 65.3, 100 even. When in doubt, add up your percentages. That should equal 100%. So oxygen is nearly 2/3 of that entire compound. Are there any questions on how to do that? How are we feeling? All right. Okay. Let's get to the last lesson for today. We have 20 minutes left in class. How to calculate empirical formulas. All right, so when a compound's percent composition is known, its formula can be calculated. So we're going to do an example here, and as I've done before, I'm going to give you the step-by-step procedure on how to do it, and that will be it for today, okay? So here is our example. You have 100 grams of sulfur trioxide. you first need to calculate the percent composition. I'm going to let you guys do that now. Psst. Sulfur's 32.1, right? Mm. Did you guys get 80.1 grams per mole? Okay. Now, you need to find the percents. So let's do that. All right. You have 59.9 for oxygen and 40.1 for sulfur? Huh? Okay, so now, guys, let's apply that to the 100 grams. If you have 100 grams of it, listen up. This is where it can get a little tricky. If I give you a total of 100 grams, pay attention. If, oops, error. There we go. If you have 100 grams, man, why is my computer acting weird? Okay, I think I'm good. And you have 40.1% of it is sulfur. How much of that 100 grams is the sulfur? That's right. Sulfur will equal 40.1 grams. And Carson, what percent of it is going to be oxygen? That's good. That's basic algebra. Like Nick said earlier, oh, it's 100 grams. It's easy. Just like 100%, 100 grams makes it very simple. So you have 100 grams, or you have 59.9 grams of oxygen. You have 40.1 grams of sulfur. Okay, now, next step, next stage. Convert the masses to moles. So you all have 40.1 grams of sulfur. You guys have 59.9 grams of oxygen. What conversion do we use in our arsenal of conversions to convert the mass into moles? Francis? Yes, ma'am. Molar mass for both of them. The molar mass of sulfur is 32.1 grams per mole. Carson Cheeseman, where am I going to put 32.1 grams? On the bottom or on the top? That's right. Grams of sulfur cancels out. This is a division problem. Hey Siri. Hey Siri. What is 40.1 divided by 32.1?
40.1 divided by 32.1 is about 1.2492.
So we'll say 1.2 moles of sulfur. Jade, what is the molar mass of oxygen? Okay, 16 what, Jade? And where do we put the 16 grams, top or bottom? Very good. Hey Siri, what is 59.9 divided by 16?
59.9 divided by 16 is about 3.7437.
So we'll say 3.7 moles of oxygen. Y'all with me so far? Anybody got fallen off the train? David?
What about the sig figs?
We're not done yet. We're going to consider sig figs at the very end. At the very end, we're working our way there. Okay, are there any problems with converting the masses to moles? Okay, the next step is currently your ratio of sulfur to oxygen is 1.2 to 3.7. That's the current ratio. We can't do that. They have to be whole numbers. We can't have decimals, so that just won't do. So here's how we solve this problem. You will divide both of those numbers, 1.2 and 3.7, by the smallest of those two numbers. Divide both numbers by the lowest of the two, by the lowest number. And what is the lowest number between 1.2 and 3.7? Of course, it's 1.2. So you're going to divide both of them by 1.2. So what is 1.2 moles of sulfur divided by 1.2? That will equal 1 mole of sulfur. And what is 3.7 moles of oxygen divided by 1.2? That's going to be 3. Yeah, that'll do. So if I were a sophomore in high school taking this, and chemistry is not my strongest suit, you might get a little lost right here. All right, what lowest number? The lowest number between these two. Is it this one or is it that one? It's obviously 1.2. 1.2 is the lower of the two. So you're going to divide both of them by 1.2. And so now your ratio, your new ratio, is 1 to 3. The 1 represents the sulfur. The 3 represents the oxygen. You now have SO3. Can that be reduced? So this is known as your empirical formula. Yes, Kevin?
So what was the purpose of doing this whole process?
Because the purpose is that answer might have given you the molecular formula. In this particular example, it was as reduced as you can get. But let's say we got a problem that was like S309. That would have been your true molecular formula. Then you would know that that's the actual ratio, 3 to 9. But then I would have asked you, can this be reduced? And with a 3 to 9 ratio, you would say, yes, it can. you reduce it to 1 to 3, and then you would get the empirical formula. So there's a difference. What if I were to ask you, what if this, let's put it like this. Let's say you did this problem, and it was a 3 to 9 ratio. Now, if you look up here, the problem said SO3, right? That's as low as it can go. But if your answer at the very end of it was like S309, then that would have been your molecular formula. So imagine that you get a problem on your test, and it asks you to do something like this, and it has several options. Which of the following is the molecular formula for SO3? And you do all this work, and you end up getting S309. That would have been the true formula, and you would choose that as like a multiple choice option. You understand what I'm saying?
Yeah, so we can get from this process either the empirical.
In this particular problem, it turns out that SO3 can't go any lower. And so you're going to say that's my empirical formula. If it could have been reduced, like I'm just saying hypothetically, let's say we did all this math and it was 3 to 9, you would say S309 is my molecular formula. SO3 is my empirical formula. This problem will give you the molecular. Sometimes they're going to be the same.
But I mean, will you be given the formula in the first place?
No. You might say that you have a sample of a substance. Let's put it like this. Let's say that the problem started off with, you have a sample of a substance. Let me see if I can find it. And the substance is 40.1 grams sulfur and 59.9 grams oxygen. Find the formula. Might be like that, where all this information that I gave you here, you might just say you have 100 grams of something, okay? A blank. You have 100 grams of X. And X is composed of sulfur and oxygen. Find the formula. And you would have to do all this. Yeah, Nicole.
So, how would you ever get the molecular formula? Because if you divide by the smallest number, then what do you always get one?
Because there's going to be a step that we haven't gotten to yet where you would actually do the molecular formula first. We haven't done that yet. Okay? That's coming. Francis?
So because we're using percentages, the fact that it's 100 grams.
That makes it easy. That was a warm-up problem. It's not always going to be that simple. It could be like 157.2, some obscure number. And you would have to figure out what percent of that 157.2 is sulfur and what percent is oxygen.
Right.
Okay? All right. So I think you guys do have some problems in your homework that are like these, but that is basically it. I think that's enough for today. We have one more thing to do, and we're going to do it tomorrow before I give you time to work on your review. It should take us, I would imagine, 20 minutes tomorrow to do this last little part, which means the other 25 minutes can be spent on your review. So here's what your homework is. I need you to look at your reviews. I want you to do your reviews. And anything that you are just absolutely stuck on, bring that problem to class tomorrow, and we'll all work it out and get the problem fixed.